Hello professors, we are group 10 and this is our submission for MLOps assignment 1. This project we have designed and implemented an end-to-end machine learning operations pipeline to predict heart disease risk. The goal of this assignment is just not to train a model but to demonstrate how our machine learning solutions can build, automate, deployed and monitored in a production ready manner. The problem we were solving is a binary classification task to predict whether a patient has a heart disease or not. We use heart disease UCI dataset which contains more than 14 clinical features such as age, cholesterol, resting blood pressure, ECG results, etc. This dataset is widely used for benchmark classification models and it's suitable for our demonstration of a real-world medical health prediction pipeline. We begin our pipeline with an automated data acquisition and preprocessing. We have the raw data is downloaded using Python scripts ensuring reproducibility. As you can see, our data has been downloaded and saved into a raw data/raw/heart disease.csv file. So the raw, this is the heart CSV disease file dataset that we have downloaded. Now let's use pre-processing techniques to optimize the data, handling missing values, categorically variations of variables and etc. So we have done a bit of a pre-processing. Now for exploratory data analysis, we analyze the feature descriptions, class imbalance, correlations using histograms and heat maps. For this, we have used a Jupyter notebook to clearly identify and quickly build all the important parts. So as you can see, we have the dataset heading. Then we have created discussed the class imbalance, created histograms. These are the histograms for all of the datasets that we are using. This step helps us to identify and understand the data and guides our model into decision-making attributes such as feature correlation metrics. Let's stop this and let's start with data training. We have created this data training file. We train the dataset into two different classification models, logistic regression and random forest. These models are chosen to compare a single linear baseline with more powerful assemble methods. Model evaluation is done using cross-validation and metrics such as accuracy, precision, recall, ROC and AUC curves. To track all the experiments and every training, we use MLflow with help of MLflow. MLflow this allows us to track all the code, all the training models, all the experiments, and for each run we log hyperparameters, evaluation metrics, trained models and plots. This allows us to compare different models and different configurations in a systematic way. As you can see, the random forest and logistic regression of whatever we have built from the start is stored over here, and we can easily track each and every model and experiment that we have trained. We can also use charts of data accuracy, F1 score, recall to compare each and every experiments that we are running and track each and every training with the help of this MLflow. Now let's move to the API development. Once the best performing model is selected, then it is served using a FastAPI based REST API. The API exposes the predicted endpoint that accepts the patient's data in a JSON format. So as you could see, our current model will be running on the endpoint 8000. To test the particular FastAPI, let's use a localized API curl call. So as you could see, we have given a localized curl call at the port 8000 with the given input data types, and then we can predict 0, the confidence is low, there is no possible risk of heart disease over here. Now let's run some basic Pytests to make sure that our code and other Python tests are running correctly. So all in the Python files we are creating 14 test cases, and all of them are passed for testing our API endpoints. To ensure consistent development and consistent environment application, we use Docker. So let's use Docker to create a central build image. The Docker image includes trained models, pre-processing pipelines, and the API code. As you can see, our Docker image has been built successfully. Let's run our API, Docker API. As we were using localhost 8000 as an endpoint, let's hit a health checkup call. As you can see, our status is healthy and our model is loaded perfectly. To ensure a better accuracy, let's hit a curl with a curl call as well. As you could see, the curl predicts correctly and the confidence is low, like we used to do with help of the FastAPI method. Let's quickly log the Docker logs as well to identify what are the logs and what are the actual post methods that we have done. For deployment, we use Kubernetes with Minikube. Firstly, let me quickly initialize the Minikube project. This process takes a bit of a time. It pulls the latest Docker image that we have built. Now, as you can see, our Minikube has been initialized. Let's do a status check. Yeah, everything is working fine. Everything is configured. Now let's point the Docker CLI to our Minikube Dockers. And let's start building the Docker image inside Minikube. The build is complete. Now let's verify the Docker image. Yeah, as we can see, the heart disease API latest is there. Kubernetes manifests defines the deployment and services, ensuring scalability and fault tolerance. Now let's apply Kubernetes and deploy all the pods. As you can see, the pods are currently running. Let's wait, and then let's get all the pods and get all the services. For API access of Minikube, let's pull them in a perfect endpoint. So currently, as you can see, our model has been deployed on a Kubernetes pod with help of Minikube. The version is 1.0 and the status is healthy. Let's hit them with a post curl just to ensure everything is working correctly as expected. Oh. Oh, the endpoint is a bit different, so it's 519.4.0. Now you can see the correct endpoint. We are getting the correct predictions as we were using last, getting over there in the local environment. And so let's forward the Kubernetes port to a 8000 port so we don't get the above error again. For monitoring, we integrate Prometheus and Grafana to collect and visualize application matrices. Let me just quickly apply them. I'm asking Kubernetes to get the pods for Prometheus app. And I will be forwarding them to a 9090 port. So if we go and check our 9090 port, we should see a Prometheus coming up. So local host 9090, and you can see our Prometheus is active. Configuration load is successful. Everything is successful. Also, let's add a query to check everything is correct or not. Let's do an up execute. With help of this, we can get all the up pods and all the description about them. Now let's quickly apply Grafana. So the Grafana, and let's port them to a 3000 port for our benefit. Contacting 3000 port. So if we go localhost 3000, we will get a Grafana with us. Let's quickly attach a Prometheus to our Grafana. Yeah, we have added them successfully. Let's build a dashboard. Let's run the same query as we ran over there in Prometheus. Up. Let's execute our queries, and we can quickly see the panel. All of them are up. We can easily access them on our end. Let's see this panel. Health checkup. Apply. So in our dashboard, we have created our health checkup part. Let's save them. MLOps. Save. So with the help of this, with the help of Grafana and Prometheus, now we are actively monitoring our pods with help of Kubernetes. We have also implemented a CI/CD pipeline using GitHub Actions, which run linting, unit tests, and model training automatically on the code. In conclusion, the project demonstrates a complete ML lifecycle from data ingestion to deployment and monitoring, following the industry's best practices. Thank you for watching. Thank you for your time. Thank you, professors.